Hi guys, welcome back to the channel. In this video, we'll be discussing a key component in the artificial neuron architecture, that is activation function. In this video, we'll be going through the introduction of what exactly is an activation function. Then we'll be discussing what is the difference between linear versus non-linear relationships or functions. Post that, we'll be discussing the characteristics and the usages of a few prominent activation functions such as sigmoid, tine hyperbolic, ReLU, leaky ReLU, and softmax. Let's start by introducing what is a activation function. Activation function majorly has two characteristics. The first one is that activation function decides whether the neuron should be activated or not. The second major characteristic of an activation function is it introduces non-linearity into the model, allowing it to learn from data and perform complex tasks. Let's try to decode each of them one by one. Let's try to learn what do we exactly mean by it decides whether the neuron should get activated or not. On the left hand side, we see this particular picture is the artificial neuron architecture, which is the most fundamental part of any neural network or a deep neural network. To understand in depth about the architecture of a neuron, please refer to my video on neurons. So an activation function helps decide whether a neuron, that is this particular architecture, should get activated or not. Let's take an example to learn what this means. For instance, if we talk about a simple activation function, let's talk about a step activation function. Step activation function essentially means that if the threshold of the input given to this particular function breaches or the input crosses that particular threshold, then it will give an output as 1, else it will give an output as 0. For instance, if I take the threshold for this particular step function as 0.5, and let's say assume that the input x over here that is being passed as the input to this step function is zero point 0.9. Since zero point 0.9 as an input is greater than this particular threshold, we are breaching this particular threshold of zero point 0.5. The output y for this particular x, that is input, would be 1. This is what is meant by step function. The second scenario wherein let's take an example that the input x2, this let's x1 and y1, x2 is zero point 0.2. Since it is not breaching the threshold of 0.5, the output for this particular input given to a step function would be equivalent to 0. Right? This is the working of a step function. And if we assume for this particular neural network, step function is the activation function that we are using for an input greater than 0.5 threshold, which is our threshold, x1 as 0.9, we get an output as 1, which means that one output, meaning that the neuron will get fired or it will get activated, meaning output of this particular neuron will get passed to the subsequent neuron in the overall deep neural network. If the output over here is 0, where in the second case where the input did not breach that particular threshold, in this particular case, since the output is 0, the neuron will not get activated. That means that the output at this particular stage will not get passed subsequently in the next layers, or it will not get passed to the next neurons further. This is the meaning or the meaning of the first characteristics, that neuron decides whether the activation function decides whether the neuron should get activated or not. Coming to the second characteristic of a activation function, that it helps introduce non-linearity into the model. That is, it helps the model to capture complex data patterns hidden in the data. Without this particular characteristic, our models would be limited to solving linear problems, which isn't very useful in the real world scenarios, because real world scenarios, the relationship is very complex. What do we understand? What's the main difference between linear and non-linear relationships, which will help us understand the second characteristic of an activation function. Let's try to understand the difference using an example, wherein the use case is that we want to predict the prices of the house based on the square footage or the area. That is our target variable. Is we want to build a model to predict the house prices based on the square footage, that is area as a feature. On the left hand side, we see that we have if we have a linear relationship between price and the area or the square footage of the houses, we can solve it using directly a linear regression. We see a linear line over here saying that the relationship between price and square footage is linear. That is, price is proportional to the area in a linear fashion. But on the right hand side, if the relationship was not linear, that is, the price was proportional to the square of the area, and the relationship was not linear, I need a function that can help understand this particular pattern and understand that the relationship between price and area is not linear. I cannot do it using a linear regression. I need a function that can help me understand this particular pattern, which is non-linear in nature. This is where activation functions come into picture and help capture such complex dependencies between the target and the features. Coming to the first most important activation function, that is the sigmoid activation function. As evident from the graph, sigmoid activation function is an S-shaped curve where the output ranges from 0, which is the minimum one, and 1, that is maximum. Since its output ranges from 0 and 1, it is particularly used in the output layers of the neural networks for binary prediction or binary classification tasks. Let's try to understand this using an example. In our use case, let's take an example wherein any email that comes our way should be classified as a spam email or a non-spam email. Since the primary class that we want to predict is spam, we'll have this labeled as 0 and the non-spam as 1. After we have trained a model using sigmoid as an activation function, let's take an example. During prediction, an X email comes and the probability output from the sigmoid activation function is 0.9, which means that since 0.9 is very closer to 1, that is, a 0.9 probability means that is 90%. It's saying that 90% chance that the email X is a spam email because 0.9 is very closer to 1. Let's take an example wherein we have a second email Y and the probability output by the sigmoid activation function for that is 0.1, which is very closer to 0, and the probability, since it's very closer to 0 and very less, it is highly likely that it is a non-spam email. That is, values closer to 0.5 indicate uncertainty and values closer to 0 and 1 indicate confidence. Sigmoid activation function outputs probabilities if the probability is 0 near to 0.5, that is in between 0 and 1. There'll be highly uncertain. It will be highly uncertain for us to decide if the email that we have got is a spam or a non-spam, because the probability is in middle. But if the probability is closer to 0 and 1, it indicates confidence, because in this particular first example, X email had a probability of 0.9, saying that it's more probable to be a spam email since it's closer to 1. And the email Y, since the probability is very low, closer to 0, it's highly probable that it's a non-spam email. One of the major drawbacks of sigmoid activation function, that it suffers from vanishing gradient problem, especially in deep neural networks. To understand in depth about vanishing gradients, please refer to my last video on vanishing gradient problem. Since the gradient of a sigmoid function ranges between 0 to 0.25, which is very small value, while back propagating in the training process, the gradients become very small for very large or very small values of the input, which can slow down the process of training. That is, the pace at which the parameters of the neural network update to make the loss to its minimum, that process will become very slow. Hence, since the gradient value of sigmoid during back propagation ranges between 0 to 0.5, hence sometimes the model can suffer with vanishing gradient problem if it uses sigmoid as an activation function. Coming to the second most prominent activation function, that is hyperbolic tangent or tan-h. As evident from the graph, this activation function is again a S-shaped curve similar to sigmoid activation function, but the output in tan hyperbolic ranges from a minimum of -1 to a maximum of 1, which was not in the case of sigmoid, where the output ranged from 0 and 1. Hence, tan H is zero centered, meaning that its output is centered around 0. It's centered around 0 and it's symmetric around the origin, meaning that tan H of minus x is equal to minus of tan H of x. This zero centered property can help the neural network converge faster during training, meaning if we use tan H as a activation function, the learning of the model that is converging to the minimum loss happens faster as compared to sigmoid function, especially when the data is also centered around 0 or the data input data is also normalized. Hence, this function is widely used in the hidden layers of the neural network, where we need the output to be normalized in the range of -1 to +1. While tan hyperbolic is tries to mitigate the vanishing gradient problem because of its zero-centered nature, it is not totally immune to vanishing gradient, because for extremely large or small activations, the gradient again goes approximately to 0 for the tan hyperbolic function, which is called as a gradient saturation problem. Hence, as compared to sigmoid, it helps mitigate the vanishing gradient problem, but it's not totally immune, because for very large and very small activations, still the gradient nears to 0. Coming to the third most prominent type of activation functions, that is rectified linear unit or ReLU. ReLU function is a piecewise linear with threshold at x equal to 0. What do we understand by this? If we see at a threshold of 0, that is on the right hand side of 0 in this particular part, the function is linear in nature. Whereas on the left hand side, it's stagnant at 0, which is non-linear, which means that it is piecewise linear with a threshold at x equal to 0. Next, coming to the range of rectified linear unit, ReLU is 0 to infinity. That is the minimum value of the output of ReLU is 0 and the maximum is infinity, based on the function that we see over here, which says that ReLU of x is max of 0 and x. Let's try to decode this. It says that the output of ReLU activation function would be x when x is greater than or equal to 0. It will be equivalent to the input if the input is greater than or equivalent to 0. If the input is less than 0, if x is less than 0, the output will essentially be again 0, which is evident from the graph. If you see any value of input less than 0, we have the output fixed over here. The output fixed to 0 for any value less than x equal to 0. Let's take an example over here for a value x greater than 0. Let's take x is 2.5. Since it's a linear function, the output would also be equivalent to 2.5. This is the output structure of a rectified linear unit. It's evident that ReLU is simple and computationally efficient as compared to the functions that we just saw, that is sigmoid and tan hyperbolic. It's very simple to understand as well, because for any value greater than or equivalent to 0, the output would be equal to the same value, else it will be 0 if the input value is less than 0. ReLU is commonly used in hidden layers of a neural network, especially in deep learning architectures like convolutional neural networks for image processing. The problem with ReLU is it sometimes suffers from dying ReLU problem, where the neurons may become totally inactive and output a value of 0. Let's try to understand how and when this happens. As we already know, the ReLU activation function outputs a value of 0 if the input to the activation function is less than 0, right? In a particular scenario, if we say that the input to the neurons or the activation function is consistently less than 0, it means that consistently it will output 0 values. Outputting 0 values means the neuron will become inactive. it will not fire, which means that the learning of the neural network would stop, which is this particular problem is known as dying ReLU. The positive point about ReLU, unlike sigmoid and tine hyperbolic functions, is that ReLU does not saturate for large positive values of x because it ranges from 0 to infinity. The output ranges from 0 to infinity, which means that it does not suffer from vanishing gradient problem as to the same extent which sigmoid and tine hyperbolic experience. Coming to the fourth most prominent type of activation functions, that is leaky ReLU. Leaky ReLU is also a straightforward implementation, but it requires just a minor modification to the standard ReLU function that we saw. Leaky ReLU was introduced to address the dying neuron or the dying ReLU problem that we just saw. Why was this problem happening? The only reason for the dying neuron problem was this particular part in the graph of ReLU function. That is, ReLU outputs zeros for all negative inputs. If consistently there were negative inputs, the outputs will again be consistently zero, which will make the neurons inactive and hence the learning will stop. To avoid this particular problem, on the left side, that is f of x is 0 for any x which is less than 0, leaky ReLU introduced this slight modification wherein it had a small non-zero value for as an output if the value of input is less than 0. This slight modification of having a non-zero value instead of a zero value for any input less than 0 addressed the dying neuron problem. Coming to the last activation function of the video, that is softmax activation function. Softmax activation function is commonly used in the output layers of the neural network, where the goal is to predict the probability distributions of multiple classes. That is, if the task at hand is a multi-class classification, softmax is the most prominent activation function that has to be used for it. Softmax activation function transforms the raw output scores in the form of probabilities. It does so by an internal normalization process which ensures that the output probabilities of each and every class lie between 0 and 1, and that the sum of probabilities of all the classes sum up to 1. Right? Let's try to understand this using an example. Let's say the use case at hand is we want to do a sentiment analysis of any e-commerce website comment. The comment that a customer posts regarding a particular product, we need to do a sentiment analysis of that particular comment. We want to classify the comment in 3 categories. That is, it should either be a positive comment, or it can be a neutral comment, or it can be a negative comment. So you see, we have 3 classes. Hence, this is a multi-class classification use case, and we'll be using a softmax activation function to predict of the 3 classes the particular comment which we want to know the sentiment of the 3 classes, which class the particular comment lies in. Either is it a positive sentiment comment, or is it a neutral sentiment comment, or is it a negative sentiment comment. Suppose that we have logits, that is the outputs for each of these 3 classes as 0.1, 1.2, 0.9 and 2.5 for each of the 3 classes. Now, what does a softmax function does? As we just discussed, it converts these logits or the outputs into probabilities and normalizes the probabilities such that each class probability lies between 0 and 1, and the sum of all the 3 probabilities for these 3 classes should be equivalent to 1. This is the formula that we use for softmax function, and we apply this for normalization for all the 3 outputs or the logits. We get the probability for the positive class as 0.185, the neutral class as 0.137, and the negative class as 0.678, which means that the comment that we were to classify using the sentiment analyzer is a negative comment because the probability is highest for the negative comment, that is 0.678. And the last point over here, if you sum up all these three probabilities, it will be equivalent to 1, which we discussed that a softmax function does a normalization process in such a way that the sum of the probabilities of each and every class should be equivalent to 1.
Please do not forget to like the video and subscribe to the channel for more such informative videos related to artificial intelligence. Thank you.